Lifecycle management, and it was from a quite high-level perspective, but also some sneak peeks into the tools to see what questions they can answer and what types of analysis that you can perform with them. So today, being a technical seminar, I'm going to be a little more technical, and this will more be like a training session, even though you will not have the possibility to work yourself here on OPUS. But I'm going to break down for you more exactly how the tools work, how you build up a model in the tools, and how we are going to interpret the results, etc. So it will be, you're hereby warned that it will be a little more detailed level. But first of all, I introduced myself yesterday, you can do it again. My name is Jonas Rosayev. I'm a senior product expert at Systicon. Started back in 2006. With product development, training and consultancy. At that time I was involved in programming in the OPUS Suite tools, in parallel with conducting training and also using the tools in various projects. Since then, I mean that's almost 17 years ago, I have learned a lot during this journey. I have a Master of Science in Systems Engineering, so that means that when starting at Systicon, I already had some university background in mathematical modeling and optimization, operations research, and how to translate real-world problems into mathematical models. That was something that really fascinated me, and after working 6 years from another company, I found out that there was a spot open in Systicon, and Systicon just worked with mathematical modeling and building tools like OPUS Suite, where you can really apply these knowledges for real. So that was something that triggered me to start at Systicon. But during my 17 years at Systicon, I have learned a lot about the field in which we are operating, so to speak, the field of lifecycle management, logistic support analysis, RAM-C, etc. And that has been very interesting journey, I say. So now it was a long time since I did any development. There are people at Systicon that are much better than me to perform computer programming, but I have taken more and more interest in the questions that are addressed by OPUS Suite, and how do you really apply real lifecycle management in reality, in the business context, and also how the tools how they fit into that process, because the tools, OPUS Suite does not exist because they are fancy tools. They exist because they provide support and solutions to real-world problems that you are probably all familiar with, being on the supplier or manufacturing side, on the operating side. Applying lifecycle management in the real context is demanding, but also very necessary. So to help customers and users to see how they can use the tools in the best possible way to get values for that, and how they can apply in that context is something that I spend a lot of time on. And also on the reverse side, learning from our users, from the real world. What do the tools require in order to improve and provide even more values to the user community? Because we learn as well from the real world what analysis tools like OPUSuite needs in order to be effective and bring value. So, with that being said, I could, after almost 17 years, say that I'm pretty experienced OPUSuite modeler and tutor. You'll be the judge of that after these 2 days. But also how to apply the tools in the analytical context of lifecycle management. The agenda, I think you have it printed, maybe, yes, you have all the slides printed in your binders, you find them. So today, we're going to start off by an OPUSuite overview that will, again, describe what OPUSuite is and its role. And then we're going to get into the nitty-gritty details by showing you some of the main building blocks in the universe of OPUSuite and how you put together a basic model. So with the purpose that you would get a feel of what it would be like to build up a model from scratch in OPUSuite and get the first result. This is something that we will start before lunch and continue after lunch. Then we will devote some time at the cost model of OPUSuite, how it can be used in various ways and how it should be interpreted, as well as the performance, because this is something key in the notion cost effectiveness, cost versus performance. We're going to finish off today with the first step of expanding the model. You remember yesterday I showed you at the core of the OPUSuite, you have the basic model and then you can expand it gradually. And this is what it's all about. We will start with building a basic model and we will take one direction, the direction of preventive maintenance and resources, just in order for you to get a flavor of how you continue to build up this fairly basic model. Lunch is between 12 and 13. I don't know, Yang, if there's any specific details around that to communicate. Yeah, we will see what happens at lunch. And then we have 2 20 minutes breaks in the afternoon as well. And closing off the day with some question and answers, if there are any, if I haven't been perfectly clear. Tomorrow, we will bring our model into the dimension of time and simulation. We will see what it is to build a simple mission profile and how to evaluate the results over time. We will also see some other aspects that can and will vary over time. After that, we take a jump into the cost world and we'll talk about life cycle costs, LCC modeling. Some basic rules of thumb when it comes to life cycle cost modeling and what you should keep in mind. And also exemplified by a model in the tool CATLOC, which is a cost analysis program that shows you how that is built up and what you can do with it once you have your cost model in place. We'll finish off the second day and the whole technical seminar by a presentation on how we can use Opus Suite in PBL contracts. I touched on the subject yesterday, very briefly. Now we will look at a more detailed way, how this could be used and what the benefits of doing so that will give. Also, we have lunch and breaks, so that you won't get too tired. And finishing off with question and answers at closing them. So, any questions on the agenda? All right, the seminar disposition, it will be that I will present, I will explain how to explain the building blocks and how to interpret them, and then we will do some modeling in the tools. Like a TV chef, I have pre-prepared a lot of models, so you won't be sitting here watching me writing numerous lines of data in tables. That is not so funny. So, but still we will be able to see in depth how various concepts are built up. And we will of course focus on maybe what's more interesting in context like this, on results analysis, what results are provided by the tools and how you interpret them. And I would also like to introduce to you an opportunity to try on Opus Suite yourself. Normally when we have a training session, we have maybe a group of 8 people who is attending a 3-day course, and everyone is working with their computer and there are exercises to do, and I would go around and help you out and make sure everybody finished the exercise. This is not possible, not during 2 days, and not with this important number of people here. So I'm very happy to see so many of you here, but that means that we will not have the hands-on experience from your side. But we would still like to offer after the seminar, if any of you would be interested to test Opus Suite and play around in a virtual environment provided by us over the web, you are very welcome to do so. All you have to do is to go to our website. We should have had a QR code or something here, but to our website and fill in this form and express your interest for this, and we will get back to you. And this offer is valid only for the month, during the month of June. So when you have this all quite fresh in your mind. So something I would like to share with you already now. Okay.
Maybe you can say that the examples from the course were also.
Yeah, exactly. So, good point, Oscar. Because then you will find yourself in an environment with the 3 tools, OPUS, SIMLOX, and CATLOC, and the files that we are going through during the seminar, so that you can go back to them, investigate, and play around with them as you seem fit in your own pace. Good point, Oscar. All right, let's then take on the first step, Opus Suite overview. And this is something that you might recognize from yesterday, where I describe as the play field or the playground for Opus Suite, and also, of course, then for logistics support analysis and lifecycle management. These 3 entities are key: the technical system, the support solution, and operations. They are vital in order to understand the relation between things like readiness, mission success, and cost. And they are also vital in order to understand how you can affect readiness, mission success, and cost. Because it's through these three entities that you have the possibility to impact these values. So if you have, for example, a very poor system with poor RAM properties, you can compensate that to a certain extent with your support organization. Or maybe you have an operational profile that is very forgiving and is not so demanding, so that poor RAM properties will not be an issue. But if you have a very good technical system with good RAM properties, you might have less harsh requirements on your support organization because the system will not require that much support. But on the other hand, if your operations are very tough and very demanding, that still might be the case that you will, despite a very reliable system, need to beef up your support organization in order to respond to your highly requirements on operational activities. So you see there is an interconnection that goes through all the ways between these three entities, and that's why they are so important. You can't not only look at one of them and think that you will accommodate system effectiveness or cost effectiveness by just addressing one of these three. You need to look at the whole picture. And for me, sometimes this is the whole system. It's not the helicopter back there. The whole system is the interaction between these three entities. That is what we say is the system approach to perform logistics analysis and logistics optimization. You need to take on the system approach. You cannot be cost effective by only looking at one of these entities. So, and these three entities, they can be measured by some key performance indicators, some KPIs, in order to assess their goodness or what is their quality, so to speak. So the system itself can be, if we are talking availability performance again, the concept which we were talking about yesterday, and I explained the difference between technical performance and availability performance, where technical performance are more features and things the system can do, and which we leave out in this context now, because now we're talking about availability performance when the system can perform, not what the system can perform. And availability performance, you can say, from a system perspective, is dependent on the mean time between maintenance and the mean time to maintain. These are the two factors that affect when the system is not operationally ready. The same thing with the support effectiveness, given that the system is not operationally ready and needs to be maintained. How long time is the support response for doing that? Because mean time to maintain, that is the value, given that you have all the things you need to do the maintenance. You can't never fix the system faster than MTTM, regardless how many resources or spare parts you have. But what challenges here is how long time do you have to wait for the correct spare part, for the resource, for the administrative work, for clearance of material, etc., etc. This will determine the total downtime of the system. And of course, this is highly dependent on support solution, how you have decided to shape your support organization, how many chains of levels of support is in action, etc. But none of these, for the system or the support organization, it will always come down to what do we need to do? Why do we need to be available? Why do we need to fast get back in operational condition? Well, that depends on our operational requirements, the operating time requested, the success rate on our missions, etc. And that will also determine how many systems that we need in order to fulfill our operations. Because if we have a fleet of 20 systems, of which 10 are always on maintenance, that requires probably that we will need to buy 30 systems to have enough systems to cover up for all these that are in maintenance. So that is also a factor that needs to be taken into account. But these numbers are not fixed. You can't fix one of them and calculate the other ones from that one, because this is an iterative work that has to be done, and you have to decide what values on these properties that are good enough for you, and then at the end of the day, what is it allowed to cost? So we could look at this from another point of view that says, like, you have your life cycle management control panel here. I am having knobs that I can turn on here to decide on the values of all these properties. You have the technical system, the support, the operational requirement, and the cost. And if you imagine, if you try to turn the knobs of all these at the same time, you will never reach a result, because everything will keep changing all the time, and you will get confused, and there will be nothing. So you will have to decide which are the ones that are critical, that we need to lock and say, this is our starting point. We don't have more money than this budget. This is an upper limit for us. Or we can say that most critical here is to get the readiness, the operational availability, or the mission success factor. And these will then govern and point out the other ones, what would be the requirements on the systems or on the support. Or we decide that the support response can't be faster than a certain amount of time. What will that impact the technical system? So this is not an exact science. This is not something to say, do it this way and it will be correct. It is a work that needs to be done. It needs to be revisited. It has to have the right people involved, but it needs to follow a structured approach. And you will, at some point in time, reach a level where you see, okay, now we're good. We think that these values are the ones that will be correct, and we can deduce the other information from that one. Let's have this as a starting point, as a working hypothesis into the next stage, always being prepared to come back and question your decisions that you did in the first place. So it is an iterative work, and the picture that Oscar showed us yesterday with the decisions, and there were circles around each phase, meaning that you have to redo it all the time. That's the complicated thing with applying analytic lifecycle management. It's not a straight path. It's not a one-way answer. But you need to work with these questions, and you need to address them, and you need to have the right people involved, and you need to know when you are good enough. And by doing that, you are already doing very well. And in this process is where we find OPUS Suite. to help you in this process, to understand the relation, the dynamics between those parameters, to understand what happens if we are increasing the mean time between maintenance. What would be the impact on the other parameters for that? Can we accept this or not, etc. Or if we are okay with an availability which is below 80%, what would that give us for impact? Or if we say we have not more money for logistic support than X billion dollars, how do we spend them in the best way? And this is a lot of information. And by informed decision support, we mean that take the information that you have. If it's very little information that you have in an early phase, that might be the case, but it's still information. Or if it's a lot of information that you have during operational phase, where you have gathered a lot of experience and a lot of information, still information. You need to do something with this information because it contains insights and conclusions. So OPUS Suite provides a model for handling this information, even if it's very little information or if it's a lot of information. In order to go to the next step, which is the analysis. Because the model serves as input to the analysis, and the analysis helps us in understanding the information and what the information tells us. It gives us results, and the results will give us then the understanding and help us to take the right decision. So this is what it's about. Informed decision support in this process of establishing analytic lifecycle management. And it is a complex picture. We saw these three entities of the system, the support organization, and the operations, but each one of these three entities contain a lot of information, detailed information about the system, the fleet size, the operations, the transport, the repairs, the tasks, the maintenance resources involved. It is, simply said, an awful lot to consider. And there's a saying that says that the devil is in the details of things. And this is very true for this case. Because it's not possible for a human being to be able to cope with that amount of information, all the granularity of it, and understand what this leads us. What is the cost? What is the risk? What is the performance? Or what is the competitiveness? Hard, a very difficult word. But given that you are a supplier and you're competing on the market with other suppliers, what is your edge? What can you? I've heard you have several customers that have said to us, our strong selling point is LCC. We can show them that we have quality products, but you also have good transparency on our LCC and a low LCC because we have worked with these. We are working with this concept, and that has won many deals for them because they can show in a credible way that they have a cost-effective system. So all these aspects rely within this information or these details. So in order to take decisions, you see this guy is coming up to a crossroad, and should he go down the analysis route or should he go on his gut feeling? He has this information. He needs to do it. He can stick the finger in the air and say, okay, I think it will be this way. Or he can choose a structured approach to the information they have and to see, okay, based on what we have today and based on this analysis, I can say that we should go in this direction. And this guy says, go there, don't guess, no. And this is also a question that we get quite often from people say, but how do I know that this will be correct if I do some study at a certain point in it? The answer is, you know one thing, and that is that it's not correct. But you have to take a decision, because everything changes all the time. So what you take decision today might be not what the end result will be. But that does not change the fact that you have to take a decision today. And you have to take it based on the information that you have today. And you can choose then if you want to take, to document or underbuild your decision with some structured approach and analysis, which you can later say, if someone said, hey, but that decision, that was not that good. Well, but we did proper analysis. This was the information we had at the time. And here are the results of the analysis. That was the only decision we could make. And you could probably get a lot more acceptance for having taken that decision at that time, because you can show that you had good foundation for your decision. Then things always happen. Things come along and things changes. That's why you cannot make an analysis, put it in the drawer and say that this will be the future. You should always take into account new information coming in, redo analysis, etc. But decisions do not wait. They need to be taken at a certain point in time, and when you take them, you need to have good foundation for what the decision that you take. Then no one can accuse you of being sloppy or having taken a decision light-weighted. So, OPUS Suite Analytical Lifecycle Management support in identifying cost-effective decisions and solutions. And we love to show this picture, and it could be symbolizing a bit what this is all about. So we have this diagram in the middle that has cost on the x-axis and performance on the y-axis. And that may illustrate that for a certain cost, we will get a certain performance. And by cost here, we could say sustainment costs. By investing in maintenance resources and spare parts, etc., and by analyzing this support organization, the system, and the operations together, we will get a certain bang for the buck, so to speak. But there are many, many ways you can place your money in these resources, and there are many ways you can get different results. In fact, there are close to infinitely, no, not infinitely, but really many combinations here. You can invest a lot of money and get poor results out of that. You can invest very little money and get better results. But how do you know what you would like to be is on the upper boundary of this cloud, which translates a bit to give me most performance for every invested dollar. When you are analyzing, you're making an analysis of the conditions that exist at a certain point in time, like yeah, I don't find the word for it, but still, we are analyzing how things are looking at the time. We could typically get the result like this. We are somewhere in the middle. We are not too bad, we are not too good either. So, where do we want to move? We probably don't want to take actions that will point us downwards, or that we get more cost without increase of performance, or that we get lower performance, or that we increase the cost and lower the performance as well. These are actions leading in these directions. We don't want to make them. There could be circumstances where we have to increase the costs and get some increased performance as well. Or we want to decrease the cost and accept some decreased performance. But what we typically would like to is to take actions that will increase our performance without spending more money, or keep the existing performance but paying less. But the absolute best direction to go is to increase performance while saving money at the same time. So moving in that direction to say northwest until we struck the curve. And this is symbolizing a bit what we are talking about when we talk about analysis and OPUS suite. We want to find these actions with the help of analysis and the tools. We will find these actions that helps us to increase performance and spend less money, and hence become much more cost effective. Get the most effectiveness out of each dollar spent. Now it's time to introduce the tools. We have OPUS 10 optimization software, which is used for evaluating support systems design and investments, also evaluating different system designs, technical system designs in terms of RAM properties and supportability. It is an optimization software. That means that it's built on mathematical algorithms that are calculating optimal spare parts results given the support strategy outlined in the model. This is for setting the strategy, for taking a strategical decision when coming to investing in maintenance resources and the choice between different maintenance concepts. Should we have one central store for spare parts, or should we have distributed stores for spare parts, etc.? Which is the best option from a strategic point of view? We are here calculating with average values and are making a deterministic model for the future. SIMLOX, simulation tool, the same world as for the OPUS 10, but with the difference that now we are taking this deterministic steady-state model and watch how it operates in a dynamic context. SIMLOX does not optimize, it simulates. So we see, is this strategy sustainable over time? Which are the bottlenecks that can appear? We can also describe the utilization of the system in a more detailed way, exactly when we want to use the system instead of an average utilization. We can study changes along the way. Failure rate might increase after 10 years, or we might transfer in new systems and new assets after a certain period in time. How will that change the dynamics? So we always recommend build your strategy based on OPUS 10, evaluate it in the time domain in SIMLOX to see the robustness of the solution. And then you have CATLOC, which is a cost analysis tool, as open as Excel, as I used to say. I've analyzed once the choice of mobile phone operator for Systicon using CATLOC. So you can build any cost model you like in CATLOC, but it is designed for supporting life cycle cost modeling. So it has some kind of entities and structures that is very makes it much more easier to work with life cycle cost. And the big advantage with CATLOC is that it is actually intimately integrated with OPUS and SIMLOX in order to take results from OPUS 10 and from SIMLOX and evaluate cost impact of various scenarios. So these three tools, they work closely together and provides them very good capability. And we take this picture that Oscar showed yesterday of some examples of applications of the OPUS suite through the life cycle. I want to read them loud for you right now. You have them in the paper as well. But as you see, this is just a quite small sample of things that you can, questions that you can address and use the OPUS suite through the life cycle. So it's really up to your imagination what you can do in terms of analysis here. And I can also say that during this training here now, we will focus on OPUS 10, SIMLOX, and CATLOC. But as you saw yesterday, we have also some new capabilities which have, from our point of view, filled some holes in this model picture of analysis that we would like to communicate with the products Connect, OPUS Suite Connect, OPUS Suite Insights, and also OPUS Suite Evo, because they address things that we have seen among our users are needed and requested and provide value in this analysis context. But during this seminar now, we will focus on OPUS, SIMLOX, and CATLOC. Okay.
혹시 저 에어컨이 추운가요, 많이? 이렇게? 제가 1시간에 한 번씩 쉰다 그랬는데 그냥 이번 시간은 스킵하고 바로 넘어가도록 하고, 그다음에 중요한 말을 했어요. 그래서 이거 잠깐 제가 설명을 드릴게요. 제가 아는 범위로. 왜냐하면 질문이 많이 들어오는 것들 중에 하나가 최적화라는 게 시간이 변해가면서 최적화가 가능하냐? 불가능합니다. 그래서 아까 뭐라고 했어요? 이 친구가 스테디 스테이트에서 최적화만 가능하고, 그 다음에 최적화라는 건 우리가 알고 있는 수학책에서 알고 있는 이런 어떤 컨티뉴어스한 상황들이 아니고 하나의 여러 개의 솔루션들을 조합하는 컨비네이션의 문제입니다. 그런 것들이 이제 최적화 기법으로 사용이 된 거고, 그 다음에 여러 가지 상황들이 시간에 따라서 변해갈 땐 답이 없느냐, 그런 것들을 어떻게 최적화해야 되느냐, 그걸 이제 MNS로 여기는 문제를 해결했다, 이런 뜻인데, 이 두 가지가 질문이 제일 많이 들어요. 최적화 어떻게 했는데, 무슨 함수를 썼는데, 막 이런 식으로 질문하는 경우가 되게 많은데, 그런 문제는 아니라고 이렇게 지금 답을 했고요, 이 친구가. 그래서 구분을 하셔야 됩니다. 스테디 스테이트 문제를 먼저 풀어야 되고, 그게 해결이 돼야지 그 다음 스텝으로 시뮬레이션이라는 게 가능합니다. 대신 조건은 시뮬레이션을 하기 위해서 상황들을 여러 가지를 만들어낼 수가 있다. 만약에 그게 가능하다면 여기 지금 나와 있는 슬라이드 이런 문제들을 우리가 이제 해결할 수 있다. 이런 식의 내용이고요. 캐틀락은 사실은 계산기입니다. 시뮬레이션이나 최적화가 다 끝난 다음에 그 결과들을 가져와 가지고 계산하는 역할을 하는 엑셀 시트라고 보시면 돼요. 저기에는 특별한 기능은 없습니다. 그래서 우리가 최적화라는 개념, 그 다음에 시뮬레이션이라는 개념, 이 두 가지는 구분을 하고 두셔야 되고, 두 번째 스테디 스테이트하고 시간이 변해가는, 그러니까 상황이 변해갈 때 문제들, 이런 것들은 서로 다른 문제인데 자꾸 두 개를 한꺼번에 엮어가지고 생각하시면 곤란하다. 이런 얘기했습니다. 지금 이 친구가 얘기한 거. 오케이?
혹시 그 오퍼레이션 타임이 짧으니까 그 스테이트를 반복해서 계속하면 우리가 말씀하시는 펑셔널 다이나믹 스테이트 같은 역할을 기대할 수 있지 않을까. 왜냐하면 이거를 이 모델의 장점이라고 하면 오퍼레이션 타임, 런타임 같은 걸 줄였을 텐데, 그러면 그 스테이트의 인터벌을 이렇게 줄여가면 사람들이 생각하는 그와 다이나믹한 상황에 근접할 수 있지 않을까 하는 생각. 인풋 데이터의 어떤 특정한 부분이 계속 바뀌는 걸 테니까 시간이 흐르는 따라.
그런 방법들을 하나 소개드리죠. 오퍼레이셔널 포트인데 미션을 여기로 주고 짜는 성공하면서 미션의 영역에 우리는 오퍼레이셔널 포트파일이 되거든요. 그 포트파일은 여러 개 만들어서 여기 시식해서 조정을 하는 거죠. 네, 그런 게 있습니다.
Okay, with that overview and some questions and explanations here, I think we should get started with the first topic, building a basic model. I come back to this picture again. I will do many times because I think it's important and it illustrates very well what we are doing. Building a model consists of setting up this universe step by step. It's not complicated, but it has to be done. And we will start by setting up the technical system. And I will show you how that is built up. You might remember this picture from yesterday. Start simple and gradually refine. You don't have to start with a system which is that does not have no items or subsystems. You can start on any level of details that you want, but it's more common that you start somewhere in the middle, in between here, than with a full system directly, because that could be very overwhelming and you easily might get lost in the process of all the details. So typically when you build up the model, you start with the main parts of the system, and as you get information or have information about the various parts, you gradually detail each subsystem or engine system. But a very important aspect when you are modeling your system in Opus Suite is what is the purpose of your analysis. It's not necessarily so that, because we have seen some customers, some users that think that the more details I have in the model about my system, the better the result will become. Is that necessarily true? No. It depends on what kind of question you are addressing and what type of problem you want to analyze. But it's not necessarily so that you want to have every nut and bolt and in the model, and then you will get a more accurate result. One consultancy case that I worked with, we identified a weapon system on a ship, and we saw that by addressing 20% of the items in our model, we were covering for 80% of the costs. Because these 20% in numbers of items, that was the capital items that were most expensive and most error prone. So we took out only these 20% of the items and made the analysis for these only, and we left the rest. But that is important to know, that the analysis only consisted of the 20% of the most expensive and error prone items. And that's okay, as long as we know that. And I don't think we could have got another answer to the question that we addressed if we had taken in the rest, taken 100% of the items in the model. Probably not. Probably we would have got the same result and the same conclusion. But it made the model a lot easier to do, and we get an answer quickly instead of waiting to have all the perfect information for all the details. So always think, what is the scope of the analysis, and what questions should we have answers to? And therefore I took this crash test dummy analogy. Actually, Oscar here that came up with that analogy, I think it fitted very well. Imagine a crash test dummy. What's the purpose of this model? It's to analyze how a human body works in terms of when a car crashes. Does this model, does it need to have hair color? Does it need to have blue or brown eyes, clothes, maybe teeth, not teeth? So do I need to reproduce all the details of a human being in order to get the desired result here? No, the important thing here is the limbs, the main parts of the body, to see how it reacts, and that will give us the correct answers for our analysis. So don't spend time on getting this doll, a wig or something like that, because that will not add any valuable information to your analysis. The model should fit the purpose. So, a product, now we're getting detailed. Product modeling, building blocks in Opus Suite here. We are talking about a product here. Product, that is the concept used in Opus 10. And I will come back to that later. We have tried to streamline and to harmonize the terminology with some concepts in the real world. So for example, in the standard of S3000L that you might know, the LSA standard, they are talking about products and product variants. We thought that was a good idea and wanted to reflect concepts like that in our model as well. So we have adopted this notion of a product that is like the product family, the mother of the product. And then we could derive multiple product variants from that product. A product variant is further broken down into breakdown elements. And breakdown elements are, you could call them positions or hardware or subsystems. They are placeholders or representatives for functions and items in the model.
Is there any limitation in the hierarchy, maybe 15 or 20? Is there any?
No, you can build how deep hierarchy you want and how long hierarchy.
There are so many.
Yeah, I know. The auto chapters. No, so that is possible. You can build any granularity you want and how many levels you want. But of course, it will be a more complicated model.
You just limit the learning time if you have more.
Yeah.
That's all.
Yeah. But these are, for example, this is a position, and a position does not have to be implemented. It could be like an assembly. It says this is like the overall section. Below here you will have the real parts. And this is a subsystem which is then consists of one part then on which you can collect some results and performance. So the main system will be derived from the product, but you could have some subsystem, for example, engine subsystem or radar subsystem. If you are modeling a ship is consisted often of very many subsystems. But breakdown elements that are of type hardware, they need to be implemented by hardware items. So here you can say that you have a position, a breakdown element, which is implemented by a hardware item. So for example, if we take the analogy of a car, you can say that the breakdown element is front wheel right, front wheel left, but it's the same tire that is sitting on the same. So you make a distinction of the positions, but the hardware implementing the positions is the same item. Then, of course, an item can be broken down into multiple sub-items, which are also hardwares. And you can decide if you want to have a mirroring breakdown element structure with your hardware structure, or if you want to say that, okay, the breakdown element stops here, and the sub-items are just hardwares belonging to the item, but we don't have any specific position for that. Maybe if you have an engine and you have the spark plugs, you might say that the engine has a position of the engine, because you might want to choose between a diesel engine or a fuel engine, but once you have the engine broken down, you might not have one specific breakdown element for each spark plug. You could just list them below. But if you have an aircraft engine, maybe, that's much more complicated. You might want to have continue the mirroring of breakdown elements and hardware. So what I want to say here is really that these are the building blocks in building up technical system. And as you pointed out, you can do how many levels you want, how many positions you want. And you can also choose if you want to use the concept of breakdown elements or only hardware. That's okay also. So there's a lot of flexibility of building up product breakdown in Opus 10. So, for example, if we have an engine system that consists of these positions, and we have hardware consisting of these items. So here you can see here's a structure. Here are single items, and then you have two more complicated hardware structures. Together, they will look like this. You will have realized the positions by using these hardwares, and you get the resulting product breakdown. I hope it all makes sense. So then we come to the first. Let's look in Opus Suite so we can see how this really looks in the tool. So for those of you who have never, I need to. for those of you who have never seen Opus Suite, now you don't see the top of it because I will do like this, it will be easier. So Opus Suite is a tool that Opus 10 in this case is a tool that you have them installed on your laptop. You don't need any server access or any online resources. It's used a lot of in defense context, so you need to be working offline locally on your computer. Therefore, it's a standalone application which runs on a regular PC. When you open it up like this, it's empty. You could either start from a blank file, which allows you to build your model from scratch, or you can open up an existing model, which we are going to do in this case. Like I said, like the TV chef, I already prepared a little bit in advance, not to bore you with too much data entry here. So I open up product modeling. So here is the interface, and here is our product already built in here. You can see that there is a set of tables out here. All this information is existing in this file that we opened here. So it's a self-contained database, you can say, that is not very big. You see here the size of it, it's very, very, very small. But you could also interface with external systems. Here, import from other text files, JSON format, or from a database, SQL Server, Access, any major system. But as it's a lot of defense customers using this, it needs to have a format that can be used on a restricted computer which does not have any access to any external resources. So therefore we have this built-in database format. And you can see here are our groups of tables. I think maybe this is very small for you in the back to see. See if I can increase the resolution. Now it's better maybe. So here we have the tables that build up our product variant. Here we have the tree view that describes our product, and we can also then in parallel see the tables that we fill in. So here is the product, and we just defined it product. I can easily edit these tables. So if I want to say have second product here, I just add my second product and it will appear here. Of course empty because I have not added anything to it, but this is typically how I add. I can add my second product as a description and it will appear here. So this is how you enter data in Opus Suite. Then we have the product variant, which is here then derived from the product, and we have variant A. I could easily create a variant B, which is also derived from product, and then suddenly I have variant B here as well. I could say that variant B also is derived from variant A, and suddenly I can see I have all the properties of variant A below variant B. So in that case, it's very good if you have multiple products that inherit the properties from each other. We have a list of breakdown elements, which are listed here in this table. So this is the format that you input data into Opus Suite. It is to insert in table format. And it will be displayed as you enter things in order to understand what you're entering. So if I look here on the breakdown element structure, I just get the whole breakdown element here. The product breakdown. I will remove some of the SIMLOX columns in order not to confuse you. So here I describe, it's in a relational format, mother identifier, sub-identifier, quantity per mother, etc. So this is fairly straightforward how I build up the product. Possible also to copy-paste in from Excel. If you have your breakdown in an Excel sheet, you can just copy-paste that back into Opus 10 directly, so you don't have to enter everything line by line. And you have the product realization, which is actually then telling me on this, for this product, on this position, the position P1001, I put my item engine here. Which leads me then to the items. Here are the hardware that I define. All the hardwares, which is item structure here, that I have. And they need to be entering with the price here. Because if we are going to make spare parts optimization, we need to understand the price for each item in order to get its relative importance on the impact on the system's performance and also how much performance you get for that price. Typically the engine is very expensive. And here I can build my hardware breakdown structure. So I have the engine modules. As you see, they have just a hardware-based breakdown structure. And they all marry together then into this product realization table where I say exactly what hardware is implementing what position. And this is what I see here. So if I remove the engine here, you see there will be a red square around this position because it is a hardware position. It is required to have a hardware to implement it, and it does not have that. So I will just add the engine back, and you can see that the engine is implementing again this position. But for example, the engine system is not implemented by any hardware. So it's just a placeholder to say to us that this is where the engine system is. It does not have any, it could be a fictitious, it does not have necessarily any physical representation. So, but with this information, I can, of course, not perform any optimization. I just have the product breakdown represented, nothing more. I don't know, I don't have any maintenance policy, I don't have any failures, I don't have any support organization, I don't have any operational context. So this information is just the beginning. Any questions? Yes, please. I can show you an example of that. It is possible to model RBDs in Opus, absolutely. So I will see here if I can find, or what we call them, We call them FBD, functional block diagrams. This is a very simple case, but it is possible to build up complex RBD structures or FBD structures within OPUS suite. Sorry? This was a new file I opened. This was not the case that we built. I opened a small example of an RBD. Right, so this is another way of modeling products. It's more effective in simulation world because you can switch between different functional operational contexts. But here we have a chapter which says FBD, which says structure, parallel, where you can model series structures, parallel structures, etc., and apply them to your product variant. It is a bit more advanced, so I won't go through it now, how you do that. It's more complex, but I can tell you that there is a lot of possibilities here in order to model big FBD structures. Is that an answer to your question? Mm-hmm. I'm not sure I fully understand your question. I don't know, Young, if you could help.
뭐 아무튼 네. 그러니까 그거 나중에 데모를 보여드리면 될 것 같은데 질문 아마도 뭐 선생님이 몇 배네 가격은 올라가는 당연히 이중주 올라가는 아무튼 되게 좋아서 따라하는
Okay. Okay. Good. Thanks for the question. It's good that you're asking. Any more questions while we're at it? Okay. Then we continue to the next step. I don't know, let's see if the presentation works in this resolution. Well, it works. Good. Then we can keep it like this. So let's come back to this picture again. Now we have modeled our product breakdown structure and the hardware items that are implementing it. Now we need to describe what can happen to this product breakdown or to this product. And that is something we call events, event modeling. And one event that can happen, of course, is failures. You can describe these failures as most commonly as operating hours. How often does a certain failure occur based on the operating time of the system? But you can also choose to describe it on calendar hours. And these two are defined, calendar hours and operating hours, they are defined as default in OPUS. But you can create your own operating parameters as well. For example, if we are talking about trains, most failures are described by kilometers and not by operating hours. If we are talking about aircraft engines, they have some failures that might occur based on engine cycles, etc. You can describe any type of failure unit of measure as you want. The failure can then be assigned to some part of the product. You can assign it to the breakdown element, or to the hardware item, or to the combination of breakdown element and hardware item. So, for example, if you have a failure that always is applied to the front left tire of your car, you would apply that failure to the combination of position front left and the tire. So you have that freedom to decide how do you assign the failure. Another event that can happen to your product is, of course, preventive maintenance. Same thing there, you can define preventive maintenance based on calendar hour, operating hour, kilometer, engine cycles. I know that there is a lot of overhaul assigned to engines, aircraft engines, based on the number of cycles they have done, etc. And you can assign it to the breakdown element, the item, or the combination of both. Now there are more events that can happen to a product breakdown, of course. When we come into the simulation world, you could also assign things like damages. But, for example, bird strike, that is not too infrequent when it comes to aircraft engines. So that's also another type of event. But if we start with the most basic ones that are applied here, and which are driven by maintenance and the inherent properties of the product, these are the two main. And what typically happens when these events occur is that you have the system in operation. The event occurs, it's either failure or preventive maintenance that triggers some kind of repair action if it's a failure, or the preventive maintenance is triggered by the schedule because we have reached the limit of the interval and the preventive maintenance is due. This will lead to a maintenance action, could be the same action depending on what type of repair or what type of preventive maintenance action that takes place. And once the maintenance is done, the system is back in operational condition again. So this is roughly the simplification of the process. So we talked about how to model the failure and the preventive maintenance. We can now talk about how we model maintenance. And there is a concept called tasks, which is a maintenance task: repair, overhaul, inspect, whatever you want to call it. Tasks can be put together into something called task package. If you, for example, you know that the specific failure requires a set of tasks to be done, you can say it's a task package. And then we have something called a maintenance activity, which is a larger activity, typically when it comes to overhaul and preventive maintenance, which can consist of a mix of other maintenance activities, task packages, or tasks. So these are the maintenance entities in OPUS suite.
Sometimes the kind of maintenance plays in different places.
Yes?
Therefore, what it is.
You mean different locations in the support organization? Absolutely, and we will come to that later, exactly where these are performed.
This is one place for locations maintenance activity.
Not necessarily. It could be multiple places. It depends on how you want to model it. Or did I understand you correct? Hmm? So if we go back to our model, I will now open up the case event modeling here, and we will continue to build further on our model. I will remove this functional block diagram view. And you can see now that I've added two categories, failures and maintenance. First we have the table of failures, where I define all the failures that can occur if the failure is assigned to the item or to the breakdown element or to the combination of both. So for the APU here, for example, I assign, for all items here, I have assigned the failure to the hardware. So if the hardware is installed in different places in the product breakdown, it will still be subjected to this failure. But if I would say that the APU, which is on 10.02, the failure is only affecting this position with this hardware, I would have put this in the table. Or if I would say then that the failure is connected to the position 10.02, I would have put it like that. Here you can see that there is a one-and-one mapping between failure and a hardware element. And that is, of course, okay. But I could decide to assign other failure APU to the same. So we have two different failures that can occur to the APU now. So there is not, it's not necessary that there should be a one-to-one mapping. You can have multiple failures to the same item or the same position or the same combination. So you are free to build up that exactly how you like. And to the failure, of course, we need to have a frequency. So the failure APU has the frequency of 407 occurrences per million operating IDs. So in this case, we have operating hours. That means that during 1 million operating hours, this failure will occur 407 times. And why do we use 1 million? This is from convenience perspective. So if we have mean time between failure of, like, say, 250 operating hours, failure rate is the inversion of mean time between failure. So I would get, this is the failure rate of that main MTBF. And that was a quite high MTBF, which gives us a low failure rate. And it would be very cumbersome to enter all these 0.000 in the model, so we decided to make it more readable to multiply all failures than with 1 million. So that would give us a failure rate of 4,000 per million operating hours. So this is how to interpret the failure rate here.
We usually use A.
Sorry?
We usually use the failure rate to interpret A, B-A-Y.
Mm-hmm.
You use some million operating hours
Yeah.
and a day. Equals what? When we
Per day?
the data is very 0.0001 like that.
Yeah.
So the accuracy is decreased.
Mm-hmm.
So you use such kind of million hours, operating hours.
Mm-hmm.
But in the field, we usually calculate the failure rate based on day.
Okay, yeah. I think you could probably do that as well. As I said, here the predefined ones are calendar hours and operating hours, but you can decide your own how you want to
In your
display.
case, the 24 hours.
20 per 24 hours, yeah, you could translate that into that as well. So this is per million operating hours. It depends then if you have a system that operates 24/7 or if you have a system that is operating only a short period of the day, I could say. But you could calculate that and put that in here as well, as long as you then know that the result will be based on days and not on operating hours. It's okay. So we have the failure and we have the failure rate. So now you have seen also that the nodes here had turned yellow. Here they are white, except for some of them up here that are yellow. That indicates the next thing we're going to talk about, how they will be addressed. So for example, all the failures in our model are repaired. So, and repair gives us a yellow node in the tree. If we would have said that this item is discarded, it's thrown away, then we would have had a blue node in the tree, indicating that this item is thrown away and not repaired. And if we would have items that are sometimes repaired and sometimes thrown away, it would have been green to show that this has both. But in this case, all of them are yellow because they are repaired. And you can see, before we go into the repair table, we need to go to the task table where we have inputted the defined and inputted the different maintenance tasks. So here we have defined replacement tasks that replaces the item that needs maintenance in the structure. And we have rectify task, which is actually the repair task. And we have different types of tasks here that can be used. Some of them are applicable only in simulation, and others are applicable also in OPUS here. A task needs to have a maintenance level to describe the complexity of the task. And it needs to have a duration. How long time does the task take? This is the minimum information that you need to supply the task. Maintenance levels can also be defined by you. So here we have said that maintenance level 1 is remove and replace items. So therefore, assigning all replace items on the primary part of the system to maintenance level 1 makes sense. Then we have maintenance level 2, remove and replace item modules, which are these ones. These are more complex because you first have to remove the primary item and then the module. So therefore they have maintenance level 2. And then you have the repair task that once the item is removed and replaced, it has to be repaired. So they are rectifying tasks. That has complexity level 3. Item repairs and item modules. And they are numbers here in terms of maintenance level. So once you have defined your tasks, you can assign them either the repair tasks to the failures. So when this failure happens, we need to conduct this rectifying task. And here we have the same task for simplicity for each item. And the replacement tasks, they go back to the breakdown structure here. And we need to assign a replacement task here. I don't know why they're not appearing. Oh, I was in the wrong model. Here, in the replacement task, I can replace each of them. Replace primary. So I've connected maintenance tasks to the product, and I've defined the failures and the maintenance levels here. So now we're ready to move forward to the next step. Yes? Sorry. No worries. Please.
설명을 해야 될 것 같아요. 안 하면 오해가 생길 것 같아서. 그래서 맨 순서가 있죠. 고장률만 가져온 거예요. 고장률을 가져와서 여기서는 어떻게 한다? 스텝이 어떻게 일어나는 거예요? 지금 이벤트란 말을 써놨죠. 이게 고장률이 100분의 1이네? 그럼 100시간마다 한 번씩 고장이 나네? 그게 만약에 정확하게 100시간에 고장이 나면 이런 일 할 필요 없어요, 우리는. 근데 100분의 1인데 이게 100시간에 날 수도 있고 200시간에 날 수도 있고 50시간에 날 수도 있고 아무튼 이런 상황들이 계속 일어난다. 대신 문제가 뭐냐면 고장률이 중요한 게 아니라 사건들이 어떻게 벌어지지? 그런 사건들 한번 생각해 볼게요. 단순하게 고장이 나는 사건이 있고 고장이 일어나면 반드시 뭐가 따라와요? 메인터넌스가 따라오겠지. 그죠? 그러면 고장이라는 사건하고 메인터넌스라는 사건은 어떻게 되는 관계예요? 우리 저 고등학교 때 배웠던 확률론에 의하면 조건부잖아. 고장이 있어야지 메인터넌스라는 행위가 발생이 됩니다. 그래서 지금 이 친구가 계속 설명하는 게 뭐예요? 프로덕트, 그 다음에 고장, 그 다음에 이런 고장이 있다고 가정을 하면 또 뭐가 있어야 돼요? 메인터넌스라는 이벤트가 있어야 돼요. 이걸 제가 수학으로 설명할게요. 독립적인 사건들이 계속 발생했다. 이걸 수학에서 문제하기 쉽습니다. 인디펜던트하니까 계산하기가 쉬워요. 대표적인 게 뭐예요? 우리 고등학교 때 배웠던 이항분포. 랜덤 베리어블이 뭐예요? 여기서는? 성공 확률이잖아. 몇 번 성공하지 이게? 20번 수행하면. 근데 여기 거꾸로 한번 생각해 보세요. 내가 계속 이 시험을 수행해서 고장이 몇 번 나지? 또는 이렇게 질문할 수도 있죠. 5번째 이게 고장이라면 어떤 태스크나 어떤 이벤트가 발생이 되는데 5번째 가서 4번째까지 고장이 아니었다가 5번째 가서 고장이 난다. 이런 경우 우리가 뭐로 배웠어요? 그 수학에서 그걸 뭐라 그러냐면 Geometric Distribution 이렇게 얘기합니다. 근데 이런 조건도 있죠. 3번째까지 문제 없다가 4번째 가서 고장이 나고 또 거꾸로 얘기해서 4번째까지 메인터넌스 했는데 5번에 또 고장이 나고 이런 식의 상황들이 복잡해집니다. 요걸 수학에서 뭐라 그래요? 하이퍼 지오메트리라고 해요. 컨디셔널이 조건부예요. 이런 사건들을 전부 다 조합을 해놓고 얘는 조합을 뽑아내는 거야. 이게 최적이냐? 이게 최적이냐? 이런 식으로. 물론 수학 얘기는 안 했습니다. 이 친구가. 제가 답답해서 이제 얘기하는 거고. 그래서 이런 이벤트들을 전부 다 설명을 합니다. 아주 정의를 해줘요. 그 다음에 이걸 무한히 반복을 했다고 했을 때 여기서 뽑을 수 있는 최적의 솔루션이 뭐냐? 이제 이걸 뽑아내는 겁니다. 지금 현재 상황은. 그래서 이벤트를 정의하고 그 이벤트들에 대해서 세부적인 또 이벤트들을 계속 정의를 해주는 거죠. 그래서 지금까지 하는 건 오퍼스텐 얘기하는 겁니다. 시뮬레이션까지 같이 안 갔어요. 그래서 그 앞서서 굳이 질문하시면 안 되고. 두 번째, 이 친구가 저 설명을 안 했는데 여기 저 프로덕트하고 베리언트라고 써놨죠. 그래서 이게 새로운 모델에서 RDM 모델이라고 그러는데 아마 Define Data 모델과 이런 뜻일 겁니다. 제가 알기로는. 이게 왜 이렇게 이름을 또 얘네 이 친구들이 바꿔놨냐면 S 시리즈 때문에 그래요. S 시리즈를 들어가서 한번 데이터 스트럭처를 보신 분 계세요? S1000D부터 해서 S6000까지 데이터 스트럭처에 대해서 한번 보신 적 있어요? 전부 다들? 진짜 안 보셨어요? 들어가서 제발 한번 보세요. 거기에 데이터 스트럭처가 어떻게 구성이 돼 있고 이것들을 이 데이터 스트럭처를 끌고 와가지고 우리가 분석을 한다면 어떤 식의 스트럭처를 가져와서 분석을 해야 되지? 이런 문제가 생길 거 아니에요. 그것 때문에 이렇게 바꾸는 겁니다 지금. 그거하고 잘 매칭이 될 수 있게. 베리언트란 말이 그래서 나온 거예요 지금. 그런 얘기는 이제 설명을 안 했는데 그런 문제가 있고. 두 번째, 여기 템플릿을 안 보여줬어요. 근데 여기는 오케이, 우리가 램 분석했어? 그럼 램 분석에 관련된 템플릿만 먼저 보여줘. 두 번째 스텝, 서포트를 어떻게 할 건데 템플릿을 보여줘. 이런 식으로 계속 진행이 되는 겁니다 지금 현재. 그러다 보니까 전체 다를 보여드리는 건 아니고 스텝 바이 스텝으로 지금. 그래서 이벤트를 지정하는 단계까지, 그것도 여러 가지 이벤트가 있는데 겨우 뭐예요? 고장이라는 이벤트, 그 다음에 메인터넌스라는 이벤트만 일단 지정을 한 겁니다 지금 현재까지. 그 다음에 시간을 어디로 보낸다? 시간이 없다랬죠. 스테이드 스테이트니까. 이런 일이 무한히 반복이 되면 평균적으로 어떻게 될 건데? 이게 오퍼스텐이다 이렇게 생각하시면 돼요 지금 현재. 그래서 전체적인 모델까지도 안 갔어요 아직. 스텝이 계속 지금 설명하는 과정이다 이렇게 생각하시면 돼요.
질문. 아까 그 페일리어 레이트만 여기가 필요로 하거든요. 근데 여기에 그 고장 분포를 지금 반영하는 프로세스가 들어가 있는지, 아까처럼 이항인지 또는 노멀인지 하이퍼 그런 분포인지 그런 거 없죠.
고장 정보만 가져와서
데이터 레이트만 갖고 하지 이거를 분포를 추정을 해서
분포를 줄 필요가 없죠.
근데 사실은 어떤 특정 분포를 하는 고장 아이템에 대해서는 잘 맞을 수 있고 이게 어떤 프랑시에이션이 심한 그런 상황에서는 잘 안 맞을 수도 있고, 왜냐면 이게 스테이스틱 프로세스니까 평균적으로 그렇다는 얘기니까 분포를 추정하는 과정은
다시 거꾸로 돌아갑니다. 스태티스티컬 디스트리뷰션하고 여기서 얘기하는 하나의 프로세스하고 전혀 다른 문제입니다. 수학적으로. 우리는 데이터를 관찰하는 데이터를 이용해서 지수구라는 고장을 얻었고 여기까지 오케이. 여기서 가져온 고장은 디스크리트하게 이벤트가 발생하게 되는 시간에 따라서 그럼 뭐로 따라가냐? 퍼즐 디스트리뷰션 따라가는 고장 몇 가지? 앞으로. 저는 다른 문제다 이거
Asking that we use any other failure function. We only use the failure rate in this model. So he answered we do not consider such kind of failure function.
Yeah. This is built on Poisson.
Based on Poisson.
Yes. Yes, please.
I have a several question. Can you assign the failure rate on each item? The failure rate is based on the total summation of sub-item or the failure rate of item itself. Means that the engine has several sub-items, and the engine failure rate can be total summation of these sub-items failure rate plus the engine failure itself.
Yes.
Or, yeah. Should I assign the total failure rate?
Yeah, you could do that. I think before, in the previous versions of Opus, that had to match up. So if you had the module, 5 modules below, that had to be less or equal to the failure rate of the engine. But now I think it's more independent. So you can assign the failures that you seem fit to each of the modules. So the sum, the total failure rate of the engine will be the sum of the effective failure rate of the engine will be the sum of the modules plus any additional failures that are attributed directly to the superior item. So you don't have to think about that they must match or anything. You can model the failures independently of each other, and Opus will take care of the total failure rate.
When you analysis, when you calculate the particular use of each item, also needs to separate the own failure rate of each item. So when I put the summation of the failure rate of some item, it does not match the exact use of each item.
So in that case, I think you would just set 0 on the upper ending. If you just want to have the sum of the failure rates, then you would not put an additional failure on the
Yeah.
item.
You don't have to assign a failure to the engine, the top item. You can leave that, and you can only have failures on the modules. Yes. So that is a freedom that you can do, and then Opus will, of course, see that it's only the modules that endure failure and not the top items.
Another question was the slide. Could you show at the very first, like there is MTBM and not MTBM. So you when I put the failure rate in this program, should I put MTBM and not MTBF?
The MTBF. MTBM is meant by mean time between maintenance, and that comprises the total of scheduled maintenance and unscheduled maintenance. So, but you're correct. With failure rate, it's MTBF. Yes. Then in the results, you will have resulting MTBM, and you will have also MTBF and MTBPM, mean time between preventive maintenance, as 3 separate results. But these are calculated based on your input, so you don't have to assign them, but they will be given on system level as a result.
The last question is, you said that when failure happens, it can be repaired for this part. So, is there any somewhere that I put the rate of the repair?
Yes, you could create a task package here that handles multiple tasks, and that you can say that the task package here has repair, task fraction 0, 50, and repair, and reorder 0, 50. That means that in 50% of the case you will repair the item, and in 50% of the case you will discard the item. Or you could do 90 or 10, depending on what you have. So this will be then the proportion. So 90% of the volumes will be repaired, 10% will be reordered. And you assign this task package instead. Here you see task package or maintenance activity to the failure here. Okay. Hmm? Time for lunch. Yes, good. Fits the schedule exactly. Perfect.
그 박사님 질문하시는 거하고 그다음에 그걸 문제는 아닌 것 같고 제가 봤을 때 그 정말 많은 질문이 뭐가 그러냐면 고정이 시간에 따라서 변화가 어떻게 돼요? 이런 질문하는 그래서 고정률 계산하면 우리가 MOASOFT 했잖아요. 거기서 끝난 거야. 지금 여기서 뭐예요? 고정률이 주어졌어요. 그럼 이 녀석이 주어진 고정률이 시간에 따라서 어떤 이벤트를 만들어내는데 이런 문제를 푸는 것과 지금 우리가 생각할 때 만약에 생각할 수 있죠. 주어진 고정률이 아니라 시간에 따라서 변하는 고정률을 가지고 뭔가 이런 이벤트들이 계속 발생이 된다면 박사님 질문하신 말대로 말이 되는 것입니다. 그걸 레드 연구소에서 했었어요. 초창기에 이런 모델을 만들면서 하다가 너무 복잡하고 계산이 안 되고 결과는 또 뭐냐 똑같다 이겁니다. 예를 들어서 인정한 정장을 가지고 여러 번 계산하는 거하고 시간에 따라서 변해가는 정장을 가지고 계산하는 거하고 차이가 뭐가 있느냐 시간을 많이 보내봤을 때 차이가 없다는 거죠. 그래가지고 여러 가지 이론이 나왔죠. 정리도 나오고 뭐라면 이제 OI 책을 보시면 되겠고 두 번째 시간에 따라서 변해가는 어떤 현상들 그다음에 서브옵티멀 문제가 있습니다. 궁극적으로 왜 그러냐면 이 이벤트들이 수많은 이벤트들이 생기고 그 이벤트 중에 이 이벤트는 최적이라고 볼 수 있는 게 있고 아닌 게 있고 이런 문제들이 많이 생겼는데 결국은 여러 번 해보면 결과는 다르다 이런 겁니다. 제가 하는 소리가 아니라 해보니까 다르다. 그래서 정리가 돼 있는 내용이고 그래서 제가 지금 시간에 따라서 고정교육하는 것들에 대해서 어떻게 해야 되느냐 그건 이미 한 20-30년 전에 해보니까 의미가 없더라. 차라리 이런 이벤트를 모아가지고 시뮬레이션 하는 게 훨씬 더 현실적인 답이 된다는 게 이제 그쪽에서 했던 얘기고요. 레드 연구소라는 아시죠? 그쪽에서 이미 나왔던 내용들입니다. 그래서 그런 것에 대한 뭐 이제 얘기를 하는 건 좀 그런 거 같고 이게 오소스도 아마 아까 잠깐 얘기했는데 그런 것들 우리가 했었어요. 초창기에 시간에 따라서 전장이 변해가는 것들 지금 그런가 이런 상황들을 만들어내면 계산이 가능할까 안 할까 하고 모델을 집어넣었다가 지금은 셌습니다. 의미가 없다 해봤자 그래서 빠져있는 상태로 그걸 MS에 보다 더 현실적으로 집어넣을 수 있는 방법들을 이제 많이 만들어냈다 이렇게 보시면 될 것 같습니다. 그게 이제 나중에 설명드릴 지식력이라고 해가지고 자세히서 박사님 질문하신 것처럼 화학이냐 내가 팀이냐 하이퍼 지오메트리냐 이런 것들 여기다 가정을 해야 되냐 그럴 필요가 없습니다. 이미 이론에서 뭐가 되냐면 이런 경우라면 인디펜던트한 이벤트라면 자동으로 그걸 계산해서 일을 할 수 있다는 이론적으로 나와 있습니다.
I think it's better for us to talk together. I ask such kind of a question because there are so many items, so many failure distributions. So in some cases, we can find we cannot call this kind of failure distribution is quasi. 0.0001. 0.0000000001. It is not possible.
No.
So in this case, we can use this kind of OPUS suite because it is, as you said, OPUS suite is based on Carson distribution. So in that case, how do you modify the result one? Because there are so many items, so many failure distribution cases.
Yes.
When I check the distribution function, really 30 or 40% follow Carson distribution. Maybe 60% do not follow Carson distribution in the failure rate. Just based on the plotting. We can say, when we plotting the failure distribution, point, you can follow on this is normal distribution or this is Poisson distribution. In some cases, we cannot say it's Poisson distribution.
No.
But we must calculate considering such kind of items in focus. So in the case, do we have some indication on that?
The thing with the Poisson process is that it is that you can, under some assumptions, build up a model, because in the OPUS model we have to decide what are the rules that prevail in order to perform the optimization, and that has turned out by I don't know, the guys, this guy in the US also that has made a lot of research and do some assumptions. Of course there are items that are following other distributions, but then maybe you need another model in order to analyze this, because I think there is something here with that if you can assume that failures are happening independently, that the process does not have any memory, etc., then you can say, if these conditions prevail, then you can say that the failure rate follows the Poisson distributions. But maybe there are cases where these conditions do not apply and other distributions apply. But that would probably require another model than the model that OPUS 10 is offering.
And I think that there has been also some studies on that, and you can show that what you describe has a lot, can have impact when there are only few systems. But when you have many systems operating at the same time, it will still be distributed over a big population, and that will still be very close to the normal distribution. So normal distribution will still be a very good approximation to use even when you have maybe you have parts that are in different stages of their aging and so on. But you have a population, so the mix will still be a good enough approximation to use Poisson distribution.
다 해주셨어요?
그래도 대표님이 한번 정리해서 같이 말씀해 주시는 게 좋다.
지금 저 이거 얘기하는데 추세로 실체 나와 있는데 이런 얘기하는 건데 고정이 실수해서 하더라도 계속 여러 번 반복하면 뭐가 된다?
포함선을 수렴하려고 하는 제가 보기에는
진짜
어스럼션이나 그런 가정하에 그냥 모든 걸 다 고려할 수는 없습니다.
그렇죠. 그래서 진짜 하나 놓고 이게 시간에 따라서 세세가 되는 겁니다. 고장이 몇 났나? 한 번, 네 번. 오래 이제 프로세스라고 하는 거고, 이전에 우리가 고장을 계산하는 것보다 통계가 아니고 다른 제가 계속 얘기하지만 고장이 앞으로 몇 번 날 텐데 수치가 몇 번을 날 텐데 이런 거는 이제 하나의 프로세스예요. 프로세스가 수많이 돼 있습니다. 화학식도 있고 박사님 말씀하신 것처럼 시간에 따라서 고장률만 변화가는 뭐라 그래요? non-homogeneous 프로세스가 되는 거예요. 그런 건 다 필요 없고 화학자라는 사람이 얘기하는 거에 의하면 그렇게 복잡한 현상들이 무한히 반복이 되는 거예요. 일정한 값으로 가정하고 화학적 프로세스를 서로 문제는 없다. 그럼 뭐 수준은 어떤데 수준이 저 신경 쓰지 마라. 수준은 우리가 알고 있는 MTTI도 시간이다. 그것만 써야 이렇게 그 책에 정리가 된 거예요. 이 사람이 만들려고 하나 아니고 아무튼 리서치를 하다 보니까 그런 결과를 얻었다는 얘기고. 책은 뭐라고 유명한 책입니까? 책을 아마 정리하는 내용도 보시는데 사실 이런 질문들이 서로 이해가 되는 없는 질문들인데 제일 많이 나오는 질문이라서 제가 중간에 찍어서 이렇게 쓸데없는 얘기를 말씀드렸습니다.
실질적으로 보면 우리가 사용할 수 있는 데이터가 5년, 10년치밖에 안 되기 때문에 그런 무한 반복이라든가 이런 것들이 여전히 제한은 있지만 그 수많은 그 모델 디스트리뷰션별로 저 모델을 만들 수는 없거든요. 너무 저 자체가 굉장히 복잡한 모델이라 그래서 혹시나 아까처럼 저희가 진짜 플로팅을 해보면 펑션 안 하는 것도 많이 있는데 그런 것들 어떻게 하는지
그렇죠. 수학에 얘기하면 화성은 영양분포고 이양풀로 카드로 보내도 어디 많이 보내면 정비공포 서로 왔다 갔다 하는 거예요. 추천적으로 합니다. 내용 자체는. 그래서 그런 교육과 이제 제일 많이 들어오는 질문이라서 서로 다른 문제다라는 것들을 좀 확인을 하고 싶어요. 고장비 세사는 램수 업무하고 스퀘어 세사는 지금 요 업무하고 전혀 다른 겁니다. 내용이. 제가 같은 상황에서 얘기하지 마시라. 이런 식이고요. 그래서 이게 박사님 말씀하신 것처럼 우리는 워낙 운용 자료가 없다. 5년, 기껏해가 10년 이 정도가. 그래서 어떻게 해야 되냐. 어제 제가 말씀드렸죠. TCS 문제에서 뭐가 필요하다? MSS가 필요하다 그랬잖아요. MSS가 필요한데 셀프이 때문에 관찰된 데이터가 없고 그래서 MSS 하라는 거예요. 이렇게 모델을 만들고 여러 번 돌려봐. 시간은 더 안 됐었어. 그러면 항상 현실하고 같아진다. 그게 MSS의 기본 전제 조건입니다. 우리 저 교육 시간에 뭘 배웠어요? 대조의 법칙이라고 배웠죠. 관찰을 많이 하면 어디 간다? 어디 가요? 관찰을 많이 하면 평균을 가잖아요. 평균이 뭐야? 우리가 알고 있는 현실이야. 여러분들 맨날 뭐만 계산했어요? 평균값 계산했어요. 지금까지 MTT야. 그래서 우리가 시뮬레이션을 한다는 건 실제적인 관찰은 불가능하지만 모델을 만들고 횟수를 많이 늘리면 우리가 알고 있는 현실하고 비슷해지다. 이게 통계학 책부터 이게 입장에 나오는 대조의 법칙이에요. 마치 그럼 그게 오차가 두 번째 정리가 뭐예요? 센트럴 리스닝. N을 무한대로 보면 얼마나 오차로 줄어들더라. 그런 두 가지 전제적으로 하에 우리가 뭐라고 합니다? 모델링 시뮬레이션 하는 겁니다. 게임하고 이렇게 다르나? 되는 거예요. 그러니까 MS 하는 겁니다. 지금 하는 게. 관찰은 안 되고 이 입장에서 어떻게 해야 돼요? MS가 안 돼요. 로지스틱스에 관련된 모든 문제들, 군수 문제들 우리가 관찰할 수 있는 것이 얼마나 돼요? 1%도 안 됩니다. 전직 지역에서 벌어지는 로지스틱스에 관련된 이벤트들이 수없이 많은데 그걸 어떻게 우리가 관찰해요? 상황이 틀려지고 우리가 가정할 수 있는 내용이 틀려지면 관찰은 불가능해요. 그러다 보니까 이제 MSS를 적극적으로 활용해라. 이런 식이고요. 그런 내용 중심으로 아마 좀 계속 얘기가 될 것 같습니다. 점심 식사하시고 1시 10분쯤에 다시 하는 걸로 하겠습니다. 혹시 대표님 질문 있으면 이렇게 오셔도 됩니다. 네, 1시 10분.
Can I ask now? Can I ask something, some question now? The OPUS 10 failure block diagram, you show the block diagram. How can we show the block diagram? You choose
Here,
something.
I take
Yeah.
the view and you have FBD view.
View, FDV view.
Exactly.
Okay.
So, but in this model there is no FBD, so
Okay. Yeah.
you can see everything
Yeah.
is just in series.
Yeah. Okay. In my project, we modeled a very complicated system in OPUS 10. Then we applied failure block diagram. Then there maybe I think it is error. The availability is 100 for all point. I don't know why.